Good afternoon at GMT +7. I am Thanapat Chotipun with my teammate Vichapat Phopumyen and Tapaniya Otmang. We are from Bodindecha Singhaseni School, and I would like to present some details on ILNSS network for position on lunar surface and interplanetary prototype. So let's start with an overview with some question. What is ILNSS? ILNSS is Interplanetary Satellite Network for providing location information for another deep space mission, including to planet civilians in the near future. Consists with amount of CubeSat from 21 up to 30 or more per planet. But why we need it? According to Moon to Mars mission, we have found that NASA and ILNSS has eyes to bringing back humans to the moon with Artemis project, which is going to be launched for the first flight in the next year. So, human on the moon, colonizing. But you don't know exactly location of yourself. Location is one of the most fundamental things to have in case we want to explore by ourselves. ILNSS will provide the astronaut, rovers, robot, spacecraft, or any attached ILNSS device isolated from the Earth for the short-term usage. And how will ILNSS being? First of all, ILNSS is the constellation of CubeSat on symmetric of 6 orbit parameters, 3 difference of RNN with same amount of satellites each orbit have. An example is like Galileo, one of the GNSS. The constellation is for the coverage area on the planet's surface and a little bit altitude with proximal signal and coverage area to CubeSat amount and size. In case of Lunar or ILNSS Lucius, we will fly the CubeSat at 2000 km from the surface, which can cover about 50% of lunar surface on the planet and 200 kilometers above that surface. We would like to make ILNSS network can fully cover the entire network for continuously provide location service. The thing ILNSS provides is selenographic location, which is similar to GPS, which can be transformed into latitude, longitude, or Cartesian for hopping location to another planet. Through providing location, ILNSS have to send a stream of packets to receiver inside the network as one-way communication. The packet is shown as the figure on the presentation, and ILNSS will provide stream as much precious and as fast as it can. After the receiver gets the data packets from satellites, receiver can calculate the radius of signal and will find the intersection of signal to get their location information. But as in the figure has shown the ground station antenna, which is not possible for some planet in case of deployer cannot land on the ground or is what the gas planet. So how to verify satellite location? In this case, we are going to experiment on verifying satellite location by using VRBI technique across the planet. For the Lunar, we can verify using DSN connection because Lunar is one of the Earth orbiters, so we can set the Earth as fixed location to verifying instead of faraway quasar, which satellite cannot receive it precisely because size and amount of antenna. But there's a little bit problem on time.
Good afternoon, committee. Next, time realization. Definition of time. The system time is internal, continuous, therefore no leap seconds. The basic unit is SI seconds. The largest unit used to start the system time is 1 week, defined as 604,800 seconds. The system time is counted with the week number and the seconds of the week. The 0 point is 1st of January 2000 or J2000. Next, realization of system time. The system time is realized in the concept of composite clock. The system time is maintained by a time and frequency system located at master control station. The time synchronization. Station time and the satellite time are synchronized by two-way satellite time and frequency transfer, or TWS-TFT. The accuracy is approximated to be 1 to 5 nanoseconds. Precision is about 0.1 nanoseconds. Stability averaging over 1 day, 10 to the minus 14 to 10 to the minus 15. Assume that there is no other effect than the method of the transfer. Next, time dilation. Due to the Einstein theory of relativity, therefore, if we just account for the change of time in different perspective, it will make the position measurement to be inaccuracy. Time dilation can be cut into three parts. First part is time dilation due to Earth gravitational field. Second, time dilation due to Moon gravitational field. Third, time dilation due to satellite moving in space-time. First, time dilation due to Earth gravitational field. Because of in this frame of the reference, satellite clock will tick faster compared to the clock on Earth. Time dilation due to Moon gravitational field. In this frame of reference, satellite clock will tick slower relative to Earth clock. Time dilation due to velocity. In the special theory of relativity, moving clock will tick slower compared to the clock that stands still. The total time delay or time offset can be calculated by sum of inverse Lorentz factor from all reference frames and multiplied by the seconds of 1 day. It can be approximate value about 57.685 microseconds per day.
For our satellite, we have two types of satellite of ILNSS. One is for the operation, which is called Lucius. Lucius mainly used for navigate and provide signal, and will mainly use orbit to provide ILNSS service. Lucius will compile together with Lucius D, which is deploy of Lucius. It's mainly used for deploy Lucius at the proximal time and position. Ring budget. ILNSS Lucius ring margin is about 4.9 to 8 decibel. For two parts of communication, which is ILNSS must connect the deployer and their satellite by themselves, and connect to the DSN for satellite network info and system location verification. Proportion analysis. Lucidity and Lucius has different proportion usage in the phase of operation, which can be represented to trade of usage in the figure on presentation. Lucius proportion in and after phase 4 can be reduced by using reaction wheel attached in the satellite. However, if error is too high, Lucius will use propellant to arrive faster too. For energy balance trade, due to satellite must operate 24/7 hours, so energy must be in positive trade for in case solar panel cannot produce power in an expect situation which is shown in this figure.
Next, mission analysis. Mission analysis risk. VLBI technique failed, medium. Because of VLBI technique on a satellite is in experiment. Second, less accuracy without verification is low. Because of on a gas planet, there is no surface to land on. We have to rely on absolute location instead. Third, electronic fail is low. Because of electric system on a 24/7 time Earth is not guaranteed due to delta E balance. Next, the schedule. From this paragraph, it can show you that our satellite is ready to use as close as Artemis 3. Therefore, Artemis 3 is real situation test and last adjustment. And then it can fully operate on an Artemis 4. Next, budget. From from this paragraph, we can show you that most of our satellite budget goes to navigation system, and if it costs less than more than $2 million for entire of lunar system. Next, implement plan. This is our implement plan for our satellite. Thank you. Lastly, if you have a question, it's a pleasure. Thank you.